Hello everyone and welcome back to another episode on complete reference to CUDA programming. In previous episode, we have seen the performance of the vector addition program was limited, that is 4.4 times better. The speed up that we observed was only 4.4 times. And reason I mentioned is poor utilization of the GPU. Now let's start to recap about what we have learned from the GPU architecture. So to understand that, I have drawn here a block diagram of the GPU. So we know that GPU is comprised of streaming multiprocessors and graphics processing cluster. So what is streaming multiprocessor? A streaming multiprocessor is nothing but group of cores. So group of cores is called as streaming multiprocessor, and group of such streaming multiprocessor is referred as graphics processing cluster on the GPU. So we discussed this in one of our previous episodes where we talked about the GPU architecture in depth. Now just to give a quick recap, so here I have drawn a simple architecture where there are 4 graphics processing clusters are there, and in every graphics processing cluster there are 4 streaming multiprocessors are there. Now let's assume there are number of cores per streaming multiprocessor equal to 64. So that means every streaming multiprocessor depicted here has 64 cores, and we are having such number of streaming multiprocessors equal to 16, and hence in total we get number of cores on this particular GPU equal to 1024. So this is how the number of cores are organized on the GPU. Now let's coming back to our vector addition program, where we consider n equal to, that is our input size, equal to 2048, and threads per block that we assume 1024, right, and total number of blocks that we configured equal to only 1. Now if we see this context here, we are launching only one block which carries of 1024 threads. Now where this particular block gets scheduled on this GPU, which is having different streaming multiprocessors. So when we launch one block, it will get scheduled on one of the streaming multiprocessor, and let's say it is streaming multiprocessor 0. Note that here I am having 1024 threads. So it is not like that. Here if I am having 1024 threads, part of the thread block gets scheduled on one streaming multiprocessor and remaining on the other. So one block gets allocated to only one streaming multiprocessor on the GPU. So that's why this entire block comprising of 1024 threads is getting scheduled on only one streaming multiprocessor here, right? Now how many streaming multiprocessor we have? 16, out of which how much it is getting executed, utilized? 1. So that means the utilization of the GPU here is 1/16 with respect to the streaming multiprocessor. That means out of 16 streaming multiprocessor, only one streaming multiprocessor is getting used, and rest of the streaming multiprocessors are sitting idle. Even though we have this much computing power, we were able to use only one streaming multiprocessor, and that's the reason we referred it as a poor utilization of the GPU. Right? So one way to overcome this problem is I can launch multiple blocks. If I'm having 2048 elements in my array, so rather than launching only one thread block, which is going to perform more work, so somehow I'll come up with n equal to number of threads equal to 2048, right? So what I'll do, I will create two blocks of 1024. Now one of the block will get scheduled on one streaming multiprocessor, and next block will get scheduled on another streaming multiprocessor, right? So this is a simple example that I tried to illustrate here. Now there are other limitations are also there, like how many or what is the maximum number of threads per SM. That is, there is also limit for maximum number of threads per streaming multiprocessor, right? That is one limitation. Then with respect to GPU architecture, we'll be having maximum number of threads per block. That is also limitation. Limitation is I'm saying for every GPU, different, you can say, maximum limit is there, right? So I cannot launch or we cannot schedule at a time more than 2048 threads per SM, let's say, right? That is the maximum number of threads per SM, right? Most probably on recent GPUs, the maximum number of threads per block equal to 1024, or maybe perhaps in recent GPU architectures it could be 2048. That means the block size I'm going to launch while or decide while launching the kernel should not exceed 1024 or 2048, that is specified under the architecture. Now question is how to find out all those limits, right? To do that, on this particular cloud instance, I am having this T4 GPU. If you execute this NVIDIA-SMI command, you will get the details about what GPU you have and what version of the driver is installed and what is the CUDA toolkit version is there. So in my case, if I execute this command, so I'm getting Tesla T4 GPU and the driver version is 460.32.03 here and 11.2 is the CUDA toolkit version. Now, with respect to this GPU, we need to find out what are these limits, right? So, first of all, we'll try to understand how many cores are present here and how many streaming multiprocessors are there. So, if you Google the T4 specifications, so I just found that on NVIDIA, one of the blog, that uh, this is the GPU architecture, that is NVIDIA Turing architecture. T stands for Turing architecture. We will not explore rest of the parameters because some of them are related to tensor core and somehow related to deep learning, and we will be focusing on NVIDIA CUDA cores here. And here I'm having 2560. These many CUDA cores are present. But as I mentioned, these CUDA cores are organized in terms of streaming multiprocessor and graphics processing cluster. So what we have to identify here, we want to find out how many streaming multiprocessors are present. And to do that, we can write a simple device query program here, right? And using the structure that is present in that device query program, we will be able to print all the details about this GPU architecture. To do that, I have written a simple program here, and which is going to print all the details about this GPU. If you execute this program in your local system with different GPU, you will get the properties of that GPU. So here, first of all, I'm defining a device count variable, and first of all, I'll get how many GPUs are present in this system. So as of now, we have only one, so it will return the count, that is 1. And after that, I'm printing a simple message. There are what are the number of devices present here. And if you see here, I have created a structure or variable dev prop of type CUDA device prop, right? So this CUDA device prop is nothing but a structure which holds all the details about the GPU that I'm referring. So here for loop is just to just in case if you are having multiple devices that are present in your system, so it will go through all the devices, and based on that every device it is going to print the properties of that. So this CUDA device prop is a type, and dev prop is a variable of that CUDA device prop type. Now here I am calling this function CUDA get device properties, and I'm passing the dev prop variable that are declared here, and here I'm passing the ID of that particular device. So we are having only one, so it will be always 0. And then I'm calling this print device prop function, that is user defined function here, and which is expecting a variable of type CUDA device prop, right? And now simply we have to go into that structure and print the details. So here devprop.measure will give me the measure version of that GPU. If I take devprop.minor, it will give me the minor version. .name will give the name of the GPU. Rest of the parameters are also there, but we will not investigate as of now because the separate session is required to understand what is global memory, shared memory, etc. The most important property here is multiprocessor count, right? So device prop dot multiprocessor count, which will give me total number of streaming multiprocessors present in my device. So without investigating rest of the parameters, because anyhow we are going to revisit this topic many times. So let's focus on only this value, what is multiprocessor count here. So if I execute this program now, let me save this, and if I execute this program, so you can see I'm getting all the details about this device. So this measure version is 7, minor version is 5, and this is Tesla T4 GPU. And if you see here, the total number of multiprocessors equal to 40. And in the spec, what we observed, total number of CUDA cores equal to 2560. So simply, if I'm having total number of cores are 2560, and if I divide it by the streaming processor count, so it will give me 64. That means in this particular GPU Tesla T4, I'm having 40 streaming multiprocessors, and every streaming multiprocessor has 64 number of cores, and in total I'm having 2560 number of cores, right? So that means here if I'm having 40 streaming multiprocessors, when I'm using this vector addition program with one block, one streaming multiprocessor was utilized. So out of 40, only one was utilized. So the resource utilization in that context was 1 by 40, right? And 39 streaming multiprocessor were sitting idle, right? So we have resources, but out of which we are using very few resources just because we launched only one thread block. Fine. Now you can also see here maximum threads per block is limited by 1024. That limit also we can get here, right? We have not explored what is the dimension of the threads yet, so we can skip, but maximum threads per block, that is limit is 1024. Now question is, if I'm having, let's say, 4096 number of threads, sorry, when n equal to 4096, so that is my input size. Now maximum threads per block, that is also fixed. That means I cannot go beyond that limit, and that limit we observed is 1024, right? So obviously now we have to launch multiple blocks in order to ensure that rest of the streaming multiprocessor will also get utilized. So for that, I can say here total number of blocks equal to n divided by number of threads per block, right? So n is 4096, and that is divided by 1024, which will give me 4 blocks, right? Now in earlier case, I was launching only 1024 threads, and those 1024 threads were responsible to perform addition on 4096 element. Now I'm launching 4 blocks, and every block has 1024 threads. So in total, I'm launching 4096 threads, right? So input size is 4096, and now I'm launching 4096 threads. Now how will they get scheduled on this streaming multiprocessor? Maybe one of the block is getting scheduled here, second block will get scheduled here, third block is here, and fourth block is like here, right? So now you can observe, if I increase the number of blocks with respect to the input size, the utilization is increased now. Likewise, if I go on increasing the number input size, right? If I increase n equal to, let's say, 10,000, accordingly, we will launch approximately 10 blocks, and 10 blocks will be scheduled on 10 different streaming multiprocessors. And this is how the utilization will go on increasing. So key takeaway from this episode is you have to launch multiple thread box in order to exploit the GPU's entire computing power, right? And if you go on increasing the number of threads, also work allocated per thread will also get reduced, right? If you recall, when number of threads were only 1024, every thread was performing 4 additions, assuming the n equal to 4096. But if I'm launching 4096 threads now, every thread is going to perform a single addition now. So I increase the number of threads, so work per thread is also reduced here. And this is how also we can expect the better performance. Now we have more threads which can work in parallel and less work among them, so overall runtime will be less again, right? So in the next episode, we will try to understand in using the presentation as well as using coding how that performance can be improved. Thank you.